currents, existence of degeneration, that kind of a business. And then a fourth problem is typically stuff that you have never seen before, and it's usually simple problem, but you have to make use of the knowledge of the class to make sense of the circuit. And here I stop. You tell me which of the problems that we included in this handout have something that is not clear that you would like me to address. You're awfully too quiet. There are two possibilities here. You either didn't look through the problems, which is the most likely scenario, or you look through them and you're like, I'm very confident, I know how to solve all of them, so no questions here. We should be done by now. 10:28 is a good time to let the class go.
I'm gonna say that's definitely option one.
Option one, that's what I figured out. I was still, I'm not going to dismiss the class. I hope that a few will ask questions and we're going to unfold it from there. So,
Do you think you could go over the first high frequency cutoff problem?
first high frequency. Oh, all right. This one is a good one. Because of this, I assume that you have never seen this ganging of transistors. So what this represents effectively a current mirror in which you have one diode connected branch of one device, and you have four identical devices, each one matching the one on the left. So if you ignore the bias currents, or if you ignore the base current rather, what you will see here is that the base emitter of this transistor will set the base emitter of the first device, causing certain amount of current. The same amount of current through the second, the same amount of current through the third, the same amount of current through the fourth. So in essence, this is a depiction of what you would have if you're implementing the circuit on a chip. This is how we make big devices. We take many smaller ones and kind of connect them in parallel. All the bases together, all the collectors together, all the emitters together. As a result, what we have formed here is in essence a 1 to 4 current mirror. And if you understood what I told you, if I tell you that through this diode connection device you are flowing 104 microamps, can you tell me what is ballpark the current that flows through the 5.1 kilo ohm?
Would it be 416 microamps?
Exactly, 4 times as much, 416 microamps. So the way you're going to solve this one is you have to be careful with the number of CMUs and CPIs that appear in this circuit. Notice, if you calculate the CPI of this device, since all the other four are conducting the same current, they will have their own CPIs with the same value, but four of them. You have one due to this device, one due to this device, one due to this device, and one due to this device. So the total capacitance at the base node down to ground due to CPI is actually 5 CPIs, one from the left and 4 in parallel from the right. A very similar thing will happen to any small signal quantity here you will have. If you tell me that you have a R pi coming from this device, you'll be having R pi from the first, the second, the third, and the fourth. So you will have total of 5 R pi's all in parallel from base to emitter in the small signal model. If you tell me that one of those devices has a CMU, notice that collector and bases are all tied together. If this is a calculated CMU, this one will have the same CMU, this one will have the same CMU, and the rightmost will also have the same CMU. Do you see my cursor? Okay, so in total, you have 4 CMUs if you define CMU as that of a unit device.
And you won't have one from the diode connected NPN.
You will not have one from the diode connected because you do have it, but it gets shunted out by the diode connection, yes. So if you are to draw the small signal model of this, you will see that you have a lot of things in parallel. Then you could further combine and simplify. And at the end of the day, it will become quite simple of a circuit to analyze. You have to be aware that this portion will behave as an inverting amplifier, and the 4 CMUs will experience Miller effect. So you probably that will be the dominant capacitance that will set your cutoff. And in that relation, since you have already seen this, I would like to show you or ask you whether you understand this. Do you see anything weird here?
The 2x and 1x marks.
Exactly. Pay attention. This is a shorthand notation that we use in integrated circuits. It's either a number by itself or it could be a number plus a capital A. A stands in BJTs for area. So if you see 2A or 2X, this means that this device is twice as big as this one physically. Or one way to understand it is this is simply my lazy way of me not depicting all the components. These 2X will effectively be 2 identical devices that match the size of this one, but all connected in parallel. The 2 bases tied together, the 2 emitters tied together, the 2 collectors tied together. You follow what I'm saying?
So it's just like the 4 times current mirror from previous, except shorthand.
Very good. So exactly, I was about to ask you that question. If I'm to save myself a writing and depict it for, let's say, this circuit I would like to publish in any journal or conference that accepts integrated circuits, I would never do this. I would instead do 1, and here I will say 4 next to the thing. Or for clarity, I might say 1x, 4x, indicating that the actual device is 4 times as large. And I would like to tell you that I have recorded show and tell about these bigger devices in parallel. You could find the recording. It was posted last night. You could find it in well-known secrets category. So I encourage you to look it up. Any further questions? Hold on, I have a few comments in the chat. Maybe somebody who asks for something. No, no technical requests.
Could you go over the low frequency cutoff problem number 3?
Low frequency cutoff 3? Let me see.
Yes.
All right. In this one, you have to help me out. Recognize that if you see something that you haven't seen before, you have to first decompose it into structures that you understand. Can you identify stuff that you understand?
The diff pair, M1, M2.
Yes, a diff pair, and notice that. So, in essence, once you identify a diff pair, you are saying that somehow we are creating a voltage difference on the input that relates to the input signal, and this voltage difference is converting into current. In this case, we are dumping one side and we are taking only the current variation in M2. Very good. So voltage to current action. Then what else do you see?
Two common collectors with Q1 and Q2.
A cascade of two common collectors. So a simple unity gain, just different values. I would say that probably by now you would know that as you go towards the output, the amount of current that you are drawing through those should increase if it's a meaningful circuit. All right, so very good. And you skip one action in any of those circuits. If you go through a V2I conversion, at some point you're converting back into voltage, and this conversion occurs through this resistance. All right, so you have identified the key parts. What else? Is there anything that confuses you here?
The way that the 100 kilo ohms are connected with the RG1 and G2.
You mean this and that?
Yeah.
This is a common strategy that is being used to bias two ends of a diff pair in such a way that they see the same potential. Some people tend to do the following: put a resistive divider to bias one of the gates, put a second resistive divider to bias the other. So in essence, DC-wise, they appear at the same potential. You know what I'm saying? Maybe I should draw it. Hold on. Perhaps you understand this circuit better. Can you see it?
Yeah, we can see it.
All right, I'll hold it for about 30 seconds for you to enjoy it. Maybe I'll pull a little bit so you could see the entire topology.
So what would those resistors be on the left and right? Would it be the 100K and then RG1 in parallel with RG2?
So in a simple structure like this, I assume that you will make sense of topology like this, like two identical resistive dividers, whatever the values are. The two resistive dividers completely match so that the potential DC here and here matched, putting the diff pair right in the middle, balanced gates, ready to accept a signal coupled into this and bypassing, holding this potential constant with signal, so that in essence any voltage that is applied exercises the gate on this end, redistributes the current, and then converts voltage into current. So this will be the reason of this. This is never done in practice because a mismatch between this resistive divider and this resistive divider will cause the two gates to have a slightly different offset, and diff pairs are sensitive to offset, so you could get this diff pair DC-wise poorly balanced. Because of that, this is what we do. In essence, those two resistive, this resistive divider sets the potential at this knot. What's the voltage drop across the 100K? DC-wise.
Approximately 0 because there shouldn't be much current going.
Exactly 0 because you are facing a gate of a MOSFET. If there is any current flowing through this, you have managed to damage your MOSFET. Same story goes for this one. So DC-wise, this circuit is nicely balanced because you have no voltage drop across this, no voltage drop across this. This potential is actually delivered DC-wise to both gates and therefore balancing the topology nicely. Do you understand this capacitor? What does it do for you?
Holds it steady when you're applying the AC signal to the other terminal.
Correct. So this voltage would not move with the signal, but this capacitor will couple the signal onto the gate and wiggle it about. So in order to solve the low cutoff frequency for this circuit, you effectively need to answer the following questions. There are only two capacitors for you to choose. This is not that important. You make it as large as possible. In some cases, you are matching it to this capacitor. But the real deal here is the coupling capacitor, which will receive the signal, and the coupling capacitor that will drive the load. In order to solve for those capacitances using the technique that you use in your homework, the one that directs you to a paper by Dolan and I written, tells you that you need to know what resistances the capacitors of interest are going to see. So in order to solve this problem, you have to sit at this knot and AC-wise figure out how much resistance you're going to see. Once you know that, that's your input resistance of the amplifier, and together with the source resistance determines one of the time constants of interest. The second time constant is very easy. If you could figure out what is the output resistance due to this common collector, if I specify the load for you, do I specify it somewhere? The load is 500. You should be able to form the time constants and solve the value of the capacitors in the same way you have did in the homework. Does this help any with this problem? This problem is a good one because it forces you to think of what is the input resistance, or what is the resistance if I'm facing this terminal. Figure out how those resistors combine under AC conditions. Also, it forces you to use the same information you practice in midterm number 2. What is the output resistance of a structure like this? And you already know what it is. 1/GM of this device plus whatever drives it divided by beta. Once you know this, you'll know one of the resistors that this capacitor will see. The second one is the load. Hopefully this is enough to get you going. Give it a try at home. If it's still not clear, bring it again on Friday and share your solutions, and I'll correct them for you. All right, any other questions?
Could you talk about the high frequency cutoff problem number 3?
For which one? Number
The-
3?
Yeah.
All right, this is a relatively simple one for the following reasons. There is only one device in this picture, so it will bring, in theory, two capacitance only. In practice, it actually brings three capacitance only in total. And I'll tell you shortly what is this CCI business. I bet that I expected that somebody will ask this question, so I'm going to tell you. If you ignore this capacitor for now, I hope that you understand this as nothing more than a emitter degenerated common emitter amplifier. So all of you should be able to do a small signal model for this, in which you have the input resistance, which the input resistance will be the 10K of the biasing source, in parallel with R pi effective because there is a degeneration. Then I expect everyone to be able to recognize bootstrapping input, bootstrapping effect on C pi because there is a degeneration, and to evaluate the capacitive flooding on the input node. This will come through C pi modified, C pi effective, as well as C mu, which is subject to Miller. Once you know this, you should be able to solve for the cutoff using the concept of the two-time constants. There are only two nodes in the circuit. One is associated with this node and one is associated with that node. If you could account for all the capacitive loading at those nodes and you know the resistances seen at those two nodes, you should be able to find a time constant and calculate, estimate worst case what the cutoff will be. I would like to tell you about this business here, CCI. Because of implementation, each transistor in practice always brings three capacitances, not two capacitances as we have discussed. And give me a minute, I'll draw something for you so that you could appreciate what I'm saying here. CCI, CI stands for collector to intrinsic. Can you see what I have drawn?
Yeah.
Take a good look at it, because what I'm showing here is you will see shortly where there is one extra capacitor, and it's typically a large value capacitor. Notice, well-designed BJTs are typically vertical in nature. So here you have it N. You have a well that is an N-type, and it forms the collector. Counter-doped is a second well that is P-type. And then inside you have additional very heavily doped region that forms the emitter. This creates your NPN, but notice all the NPNs are isolated from one another through A. So this diffusion, the one that forms the collector region sits in a substrate that is of type P material. And in order to make sure that this device does not talk to the rest of the BJTs on chip, this PN junction right here is reverse biased or zero biased. Because of that, right there, this large well, reverse biased, has a depletion layer capacitance. So right at your collector terminal, there is a massive capacitance that is with respect to your, typically your ground. So in a circuit like this, and this is unavoidable, CMU and CPI comes through nature, CCI comes through implementation. So if you have an NPN, you will have three capacitances. You'll have something like this, a CPI, a CMU, and you'll have additional capacitor where the other end goes to substrate, which is usually the ground of your integrated circuit. So in essence, looking at this topology, right here at your collector terminal, you have a parasitic capacitance worth 2.2 picofarad just hanging off your collector down to ground. All right, does this help? So my recommendation is for Friday, attempt this problem. All of you should be able to draw the small signal model of this circuit and populate all the capacitances that are present in this circuit. Also, all of you should be able to calculate the capacitive loading at the input node due to CPI effective and C Miller. This CCI is actually simple one. It always appears at the collector down to ground. And that's it. Hopefully, if you work out your magic, you're going to come close to the values that I have presented here. Again, the disclaimer here is the values are, I believe, accurate unless you prove me wrong. Any other questions?
Can you quickly go over surprise problem number 2?
Which one?
Surprise number 2.
Surprise 2. Huh. This one is simpler than it appears, and it's a very old problem. You were probably in your junior high when I gave this problem for an exam. Here's how it works out. See this current value at 25 degrees C is approximately 250 microamps. This allows you to write a simple expression that says, assume that the base potential is certain value, call it VBB. Assume that at nominal situation, your base emitter is about 0.7, and write equation that contains the two unknowns, VBB and RE, so that the current is approximately 250 microamps. All of you know how to do this. VBB minus 0.7 divided by RE equals 250 microamps. Now go to one of the other cases and recognize, for example, if you go to this one, 85 degrees C, this is 60 degrees more than 25 degrees C. 60 degree raise in temperature reduces your base emitter voltage by about 2 millivolts per degree C times 60, 120 millivolts. This allows you to write a second equation that says VBB minus VBE, which is now reduced. It's not 0.7 nominal, it's a 0.7 minus, give me the value. Who asked the question? Who will do some work for me here? Who asked for this question? Jeffrey.
So,
All right, so if the nominal VBE is 0.7 volt, and you increase the temperature by 60 degrees C, for every degree C, the VB shrunk by 2 millivolts. What's the VBE for that particular temperature? 85 degrees C.
is it 0.58?
I think so. 0.58 is what I also have. Can other people confirm?
That's what I have too.
All right, so here you have it. You write a second equation that says VBB, I assume, still remains the same. Now I'm not dropping 0.7, I'm dropping 0.58. Still applied across RE gives me a larger number, 270 microamps. Now you have two equations, two unknowns, and you solve them. The unknowns are your potential and your resistance. The two equation is the nominal case and the other case. And this should give you the solution. You might ask, well, if I have two equations, two unknown, why the heck do I need to consider the third case? The third case might be the worst case of the two. So you have to actually evaluate second time with this one, and notice that 20 degrees, no, it's not 20 degrees, 0 degrees C is 25 degree reduction relative to the nominal at a 2 millivolts per degree C. At this 0 degrees C, the VBE will be larger than the 0.7. I'll let you figure that one out. Hopefully this discussion helps. At the end of the day, it looks scary, but it's nothing more than an Ohm's law. Ohm's law done twice with the realization that as temperature varies, the base emitter junction will change its value away from the nominal, and you could still assume that the nominal is 0.7. Give it a try, bring it on Friday, tell me that my solutions here are correct. Ballpark. Any other questions? There's no questions, it's 11 o'clock. We're done for today. All right, now that you have seen all this, I encourage you to look at the two recorded videos that I posted last night that I found in Well-Known Secrets. One of them discusses this multi-transistor business. And give a try to all problems, just kind of read them carefully, because there might be some hidden information in there, as you have seen with this CCI business. And you attempt those that seem the most difficult to you. If you cannot handle them, bring them on Friday and we could have a discussion. All right. See you on Friday or during office hours today.
Thank you.